Hi guys, this is Surush, and in this video I'm gonna present you how fast RCNN works. Last time I talked about RCNN. If you haven't watched that yet, I strongly recommend watching it by clicking on the banner in the top right corner. But to give you a quick recap, we have an input image. Then we run an external algorithm called selective search, and it basically outputs certain bounding boxes that we refer to as region proposals. So we have the input image and region proposals as our input. Next, we extract each of them and have like 2000 region proposals where their spatial size is 224 by 224. Then we pass these region images one by one through a CNN module, and it has to give us two separate outputs. One is object class scores, and remember we have C+1 outputs, one for background and the rest for our expected objects. Meanwhile, it generates the bounding box coordinates of the object contained within the image region if it exists and the class score is not the background. Alright, so this is what we know so far, and now our goal is to make it faster. But how? Well, if we take a look closely at the CNN module, we realize that it is just extracting features from the region images. Now we might wonder, can't we do this at first and only one time per image? I mean, logically, these region images are part of our input image, and it shouldn't make any difference if we give the whole input to our CNN module, because it should again extract the features that it extracts from each region images. So the idea of improving it is by passing the whole input image, which is 224 by 224, only once instead of passing 2000 region images, which again each of them is 224 by 224. And obviously this has to improve our runtime a lot. So now let's see how fast our CNN works. We have an input image, we pass it through a CNN module called Backbone CNN, which is responsible for extracting every feature exists in the image. It produces image features. We run the selective search and it generates region proposals on these image features. We crop and warp the proposed regions, and finally we pass each of them to another module, which is just a shallow low-weight CNN module, or even just fully connected layers which are not computationally expensive, like the whole CNN module used in RCNN. And like before, it again generates two outputs. To give you an idea of why this is faster compared to RCNN, let's imagine we have this CNN module, which is ResNet 18. In RCNN, we use the whole module after cropping and warping the proposed regions. But now we have this part of the module for the backbone, which is computed only once for the whole image. And only this shallow part of the end is used for per region network. Okay, this seems pretty great. But how to make sure this part is differentiable? I mean, in RCNN, we used the cropping and warping at first, and there was not any CNN module before that. But now we have Backbone CNN here, which we need to backpropagate and tune its weight. Sadly, cropping like usual is not differentiable, and we cannot compute its gradient. So we need to find a solution. And in this paper, they proposed RoI Pooling. The way it works is that we have image features in which in every channel we have a matrix. According to the paper, we have to divide H by W ROI window into capital H by capital W grid of sub-windows of approximate size H divided by capital H by W divided by capital W. To give you a demonstration of this, imagine we have this region proposal. Looking closely, we can see that it has height of 4 and width of 5. Our goal is to crop regardless of the input size and have final output which has height of 2 and width of 2. The way we do this is that at first we divide the heights, which are 4 divided by 2, which is 2. So we draw a horizontal line, and now every sub-window's height is 2. Then we divide the widths, which are 5 divided by 2, which is 2.5, and we round it to 2. Then we draw a vertical line, and now every sub-window's width is approximately 2. And why we didn't draw a line here? Because remember, ultimately we want to do max pooling and we want our output shape to be 2 by 2. And after drawing this line, we have 3 columns. And of course we can also separate by this vertical line, which is just an implementation detail. Our next step is to max pooling the values in each sub-window into the corresponding output grid cell. So we do the max pooling and we get these 4 values, which are maximum of each sub-window. The final note to take here is that we apply this procedure for each channel separately. Alright, so by understanding this, we have a general idea of how fast our CNN works. From now on, we'll dive deeper into details mentioned in the paper. The first question we might ask ourselves is that how can we train such a model? For training this model, we should first be wondering about the CNN modules used in the architecture and the exact way used in the paper. According to the paper, they experimented with these pre-trained imaged networks, each with 5 max pooling layers and between 5 and 13 conv layers. And if we take a look at the section 4.1 they mentioned, we can see that they have used 3 models during their experiment. AlexNet, VGG-CNN M1024, which is same as AlexNet but it is wider, and VGG-16. Now let's put these aside and explain them in more detail. They mentioned in the paper that the model undergoes 3 transformations, which we already saw in the video. The first transformation is that max pooling is replaced with RoI pooling. Based on what we already should know, VGG-16 has this architecture. As what can be seen, at the top of the network there is a max pooling layer before the fully connected layers. So we remove this from the architecture and instead use RoI pooling. So basically the fully connected layer here is our shallow per region network. Selective search algorithm happens here, and these layers before are all our backbone CNN. The second modification is that currently our VGG is only useful for classification because of the classifier at the top. So we remove it and instead we use 2 fully connected layers, one for classification using softmax and the other for bounding box regression using L1 loss, which is not exactly L1 and we see it later. The final modification is that we don't have only an image as input. Instead, we have an input image and list of ground truth bounding boxes. This architecture we made now is what we already saw at the first of the video, but now it is more detailed. The next thing we need to know during training is fine-tuning for detection. At least that's what it is written in the paper, and basically here we need to know how we sample region proposals out of all of the possible outputs given by selective search, and what is the exact loss function. So let's start by the first one, which is called mini-batch sampling. Imagine we have these cat dog images and we want to use these images for training. The first thing we do is shuffling them. Then we use every two of them for our mini batches. Note that the number 2 I chose for the size of mini batch is not for the sake of explanation, and it is actually what is used in the paper. During training, of course, we select the first mini batch first. Then we pass them through backbone CNN and it gives us these image features. We run the selective search algorithm and it outputs these region proposals. Based on what is mentioned in the paper, it only selects 64 ROIs from each image. So yeah, selective search gives us like 2000 ROIs and we just sample 64 of them. But the question is, how? Do we sample them randomly? Or there's a logic behind that? Let's see. The paper basically says we take 25% of the ROIs from object proposals that have intersection over union overlap with a ground truth bounding box of at least 0.5. The remaining ROIs are sampled from object proposals that have a maximum IOU with ground truth in the interval 0.1 and 0.5. So just to give you a quick recap, we are finally supposed to sample 64 ROIs. 25% of them, which is 16, supposed to be the ones who have IOU with a ground truth of at least 0.5. And the rest 75% is the ones in this interval. The next thing we have to consider during training the model is the multitask loss, since we have both regression and classification problems at the end. We basically have two sibling output layers. The first one is vector P, which is a discrete probability distribution for our classification problem. Remember, we have k+1 categories, k for object classes, and 1 for background. The next output layer is our bounding box regression output. Note that the index k here means it is separate for each object we have in the image. And also note from the previous video that it is not what is produced directly by our output layer, and there is a transformation applied before to tweak the bounding box produced by selective search a little bit and produce these vector we can see here. And what is our ground truth? According to the paper, we have a vector u which has the exact shape of vector p, and of course all of the entries are 0 except the corresponding objects, or background if there is not any object in the image region. And we also have a vector v, which is for the bounding box regression target. Now that we are familiar with what we have at the end, the loss function proposed in the paper is having this formula. So it receives a vector p for the discrete probability distribution of classes and the corresponding ground truth u. And it also receives a vector t of u and the corresponding ground truth v. And it's a multitask loss since it's composed of two losses, one for classification and the other for regression, which I will get to these now. The first thing I want to talk about is the classification loss, which is negative log of pu. And what is pu? Remember from the vector p from the top left corner, it has k+1 entries from p0 to pk. In the corresponding ground truth, only one of the entries is 1 and the rest are 0. So we take the index of that entry from ground truth, which is U, and we grab the entry PU from our prediction and compute the negative log of that. And it is basically a cross-entropy loss function. Remember, from cross-entropy loss function, P star Y is true class distribution, which is our ground truth. And the blue PI is the predicted class distribution. So in cross-entropy loss, we iterate over k+1 entries, and each time we select our index I and compute this term here. And obviously, since in ground truth most entries are 0, the green term P star I would be 0 and has neutral effect on our final solution. But when we reach the index U that has the value of 1, then this green term would be 1, and we just calculate the log of PU and multiply by this negative value here, and we reach this formula mentioned in the paper. The next thing in the formula is this bracket thingy, which is called eversion bracket indicator. The paper says this evaluates to 1 when U is greater than or equal to 1 and 0 otherwise. It generally means if there is an object in the region, then the output of this term would be 1, and if it is just a background, then it would be 0. And the reason is obvious. We don't want to use the regressor loss for bounding box prediction when there is not any object in the region. In other words, we punish our model to be exact for predicting bounding boxes only when there is an object ground truth in the region to be compared at. And finally, we have our localization loss, which is a smooth L1 loss. What is a smooth L1 loss? It has this formula, and basically when the difference between our prediction and ground truth vector has a magnitude less than 1, then we use some kind of L2 loss, and otherwise we use some sort of L1 loss. Now the only thing remains in the formula is the lambda hyperparameter, which controls the balance between the two task losses. We actually should not care about it, because in the original paper lambda is set to 1 and both losses are equally important. And the final thing we need to know during training the model is the scale invariance feature, meaning that our model has to detect an object regardless of its scale. In other words, no matter when the object is close to the camera or far from it, it still has to predict the bounding box correctly. And there are two ways to ensure that this is happening. First one is called brute force, and the other is called image permits. In the brute force method, we have an image, we use it as our input image, pass it to our model, and it generates our output. So our model has to inherently deal with the scale invariance feature, and we do not need to do anything special. It learns it by itself. The other method, which is image permits, we modify our input before passing it through the model. We replicate like 4 versions of the input in different sizes, and we can see some kind of pyramid here, and that's probably why they call that image permits. Now, when our model produces output, this output is scale invariant because we have different scales of the input image. Note that since now we have 4 images instead of 1 image, the training time will increase up to 4 times. So to alleviate the problem, during the training we sample only one of the scales randomly, and we only use all of them during testing. Alright, now you know everything you should need to know to make a fast RCNN module. However, there is one thing we can also apply to make our inference time even faster. To understand the concepts from now on, you need to know a little bit of linear algebra. But don't worry, I explain everything necessary for understanding it. One of the problems we have at inference time is that fully connected layers have so many parameters and increase the runtime. Let's assume we have n neurons at one layer and m neurons at the next layer, and they are all connected to each other. For formalizing these two layers, we assume that the first layer is a vector x and the next layer is a vector y. And to make this equation without considering the activation function, we need to take our input x and we multiply by weight matrix, and this produces our vector y. In order to optimize our runtime during inference, we need to change this weight matrix to have the similar effect but with less parameters. The method used in the paper for doing it is called Truncated SVD. If we take a look at the figure mentioned in the paper, we can see that FC6 accounts for 38.7% and FC7 accounts for 6.2% of the whole inference time, which is a lot. By using truncated SVD, we can make it significantly less time consuming, but let's first understand what is singular value decomposition, or SVD. Let's assume we call our weight matrix W, which is m by n. We can represent this matrix as a set of vectors W1, W2 until Wn. SVD algorithm says we can write any arbitrary matrix as a multiplication of three matrices. The first one is called U, which is m by m. The next one is sigma, which has the same shape as our original matrix, which is m by n. And the last one is transpose of matrix V, which is n by n. Now let's understand what are these matrices. The matrix U, which can also be written as a set of these vectors, is what in linear algebra is called orthogonal matrix. And what is that? It means columns are orthonormal vector. And what are orthonormal vectors? It means that each column of the matrix is normalized, so their magnitude equals to 1, and also means if we compute dot product of every column pairs, it should be 0. In other words, they are orthogonal. Another feature of this matrix is that their columns can be used as a basis for matrix W. And what that means? It means every column Wi of our matrix W can be represented as a linear combination of columns of matrix U. And one thing to also note here is that these columns are hierarchically ordered, meaning that U1 is more important than U2 in terms of describing columns of our weight matrix. U2 is more important than U3, and we can continue doing this until we reach UM, which is the least important one. The next matrix is sigma. It is a diagonal matrix, and the diagonal entries are called singular values. I'm not going to explain what are singular values in general, because I have to talk about eigenvalues, and then it makes this video more related to linear algebra than fast RCNN. But all you need to know here is that they are also hierarchically ordered. So sigma 1 is larger than sigma 2, and so on and so forth. The last matrix is transpose of V matrix, which all you should know for now is that it is also orthogonal matrix. Now that we have some basic understanding of each component, we should now start understanding how they are supposed to help us. Recall from linear algebra that if we have an arbitrary matrix with shape of m by n, And if it is multiplied by a diagonal matrix n by n, then the result should be a matrix with the same shape, but now the first column is multiplied by the first diagonal entry, the second column is multiplied by the second diagonal entry, and so on and so forth. But when we take a look at our matrix sigma, we see that it is not squared and has a shape of m by n. So there are some entries in diagonal part which can be 0. So we can have two scenarios now that might be different. When the number of rows are more than number of columns. In this case, if we take a look at the matrix U, we see that the number of columns is equal to the number of rows of the original matrix, and the number of singular values is equal to the number of columns of the original matrix. Hence, coefficients of UI columns where I is larger than n would be 0. In other words, the last few columns are useless. Actually, if we closely take a look at how PyTorch or NumPy are implementing SVD, you can see that they do not even compute these last columns at all, which I'm gonna show you at the end of the video for sure. In the next scenario, the number of columns is more than the number of rows. So we might think there might be some singular values that we do not have any columns for them to be multiplied. But actually, we can prove it mathematically that these singular values are actually 0 and we shouldn't care about them at all. Okay, I agree I explained so many details now. But all I did explain was because of what I'm going to tell you now. Remember I said these columns are ordered hierarchically? Well, actually, these singular values say how much they are important. And we already know that the sigma 1 is the largest value, so U1 is the most important column. And what's the purpose of this V matrix then? Remember I said U is also a basis for our matrix W? Well, actually, this matrix is the coefficients we use to make the linear combination I mentioned earlier. Alright, I guess that's enough. We know everything we should know to use them and make our model more efficient. But how? Well, we have to use a modified version of SVD that's called Truncated SVD. And don't worry, it's much simpler to explain now that I explained the basics. Getting back to what we had, the general idea is that if sigma I is less than a certain value, then it means that the corresponding column on matrix U is not very important. And if it is not very important, then we can simply round them to 0. Now we might say, wait a minute, how does this help? Let's imagine we have this weight matrix, and somehow we compute SVD and reach these 3 matrices. Then we can say, hey, look at this small number. It is much smaller than 10.76 at the top left. So let's just remove it and consider it 0. What happens now? Removing this number means that the last column of matrix U is ineffective, since it has to be multiplied by 0, and we already know the answer would be 0. And likewise, the last row of matrix V transpose would be ineffective. Okay, then what? Let's count the parameters we have to count during computation. Before truncated SVD, in the original matrix, we have, let's say, U rows, and let's consider that we have V columns. The total number of parameters involved in matrix multiplication now, if we multiply this matrix to a layer vector, would be U times V. But what about after truncated SVD? Assuming that the remaining number of entries on the matrix sigma is T, we can say we have U times T parameters in matrix U, and t times v parameters on matrix V likewise. So just to recap what just happened, before truncated SVD we had u times v parameters, and now we have ut plus tv parameters, which can be also write as t times u plus v parameters. And how does this help now? Well, if the selected t entries are much smaller than the size of u and v, then you can test it and see how much less parameters we have now for computation. According to the paper, we can see what we already saw on the left, which indicates that 45% of our runtime is because of fully connected layers FC6 and FC7. And now, when we look at the right diagram, which is by using truncated SVD, we can see that it is reduced significantly to 17.5 plus 1.7, which is only 19.2% of the runtime. Much better. And yeah, that was all the theoretical concepts you should know for the fast RCNN. But if you'd like to know how can we use this truncated SVD in practice using PyTorch, then keep watching the video. Alright, so the first thing we need to do is to import the torch library, and let's assume we have a sample weight matrix W, which is torch.arange12. And for some reason, Torch only accepts float matrices for the input of the SVD. So we say the data type is torch.float32 or 64. And just to make it a matrix, I reshape it to be 4 by 3. And if we take a look at this matrix, we see that W is a matrix that starts from 0 until 11. And the reason I chose this sample matrix is that it is easy to follow, and we can see later why it is actually like this. So let's start by seeing how SVD works. So I just say here it is for the SVD section, and I say the matrix U and matrix sigma and matrix V equals torch.svd, and as an input I just say our input matrix is W, and that was it. And if I take a look at the U and sigma and V, we can see that because our W matrix is 4 by 3, we expect our matrix U to be 4 by 4, but it is actually 4 by 3. And the reason is that when we look at the singular values, we have 3 singular values, meaning that the last column is useless, and PyTorch doesn't compute it at all, and our V matrix is 3 by 3. However, one thing that we see here is that our singular value matrix sigma is not actually a matrix, but it is actually a vector containing the singular values. To make it a diagonal matrix, the only thing we need to do is that we say torch.diagonal or diag of sigma. And now we can see the diagonal matrix. And can we reconstruct the original matrix W by multiplying these 3 matrices? Based on theory, we should. So let's try it. I say the matrix U should be multiplied by diagonal version of this sigma matrix, so torch.diagonal of S, and multiply by V transposed. And now when we take a look at this, we see that the first entry is a value very close to 0, and our original value is 0. But the other values are actually what we have up in here. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, just like what we have here. So we can easily reconstruct our original matrix just by multiplying these 3 matrices. And yeah, SVD is so simple. But next, we want to see how truncated SVD works. So I label this section as truncated SVD. And in truncated SVD, we say that we have 3 singular values, but when we take a look closely, we see that the last one is very low value. It is actually very close to 0. So we can say that S of t is the first two values. So we select t as 2 and we say S of t is S from the first until 2. And if we print it, we see that we just select the first two values. But how can we make it diagonal? If I just say torch.diagonal of S of t is S of t diagonal and I print it, I can see that it is actually 2 by 2 matrix, but I want it to be 3 by 3 matrix. So what should I do? Well, it is actually simple, and I have to import torch.nn.functional as f. Then I can say that S of t diagonal is f.pad, because I need to pad 0 values here and here, and I say, and for the first input we say that we want to add padding for this matrix, and in the next parameter we give it a tuple and we say that do we want any padding at the left? We actually don't want that, so we say 0. And do we want a padding on right? Yes, we want. How many columns? Just 1, so it adds only 1 padding at the right, and we don't want any padding at the top, so we write 0. And we want actually just 1 padding at the bottom, so we write it as 1. So this is the padding, and then we say what is the mode. We just want it to be constant, just because we want to add the constant values, and the final parameter we say what is the value, what is the value we want to add as padding, and it is 0 because we want to just add a 0 padding. And now if I just print this ST diagonal, you see it is 3 by 3 and the last diagonal value is 0. So yeah, I can just now compute the original W as multiplication of U times ST diagonal times V dot T. And if we take a look at here, we see that it is actually very similar to what we computed here, only this value differs because we just round the final singular value, which was not very important, so we don't see any important changes, and only one minor change happens here. And yeah, this is for the sake of explanation, but be aware that we just removed only one singular values, and it actually does not make it faster because it's just only one. And if we compute it, we might see even it is having more parameters. But in real scenario, when we have thousands of parameters, I mean thousands of rows and thousands of columns, then if we select like 100 of the singular values, it should be effective. Alright, the video is finished. I hope you enjoyed it. In the next video, I'm going to talk about faster RCNN and how it makes the method even faster. If you like this video, don't forget to like and subscribe.